Hello, my name is Pavel Nomov.
And this is Wenxuan or Wendy Zhang.
Today we are going to talk about strategies that depend on your opponents not knowing something. And Wendy will give you a couple of examples of it.
On September 11, 2001, an American airplane, Flight 77 to be more exact, was controlled by two Al Qaeda agents and it crashed into the Pentagon. In the preceding month, the FBI had suspicions about the two agents who had caused this tragedy, but not enough information to actually open an investigation. On the other hand, the CIA had evidence that the two agents were indeed Al Qaeda agents and suspicions that they were about to plot an attack. However, they did not have enough power based on American laws to arrest these two agents on American land. Then the question comes up, if both the FBI and CIA had suspicions and evidence, why did they not share the information and potentially stop the two Al Qaeda agents? Well, let's take a look at this document, which was written by the Commission on Terrorist Attacks upon the United States after the 9/11 disaster. The answer lies on page 16. The FBI and CIA believe that sharing information between intelligence and criminal investigations was illegal. The Al Qaeda agents were able to attack precisely because there was an information wall between the FBI and CIA. Let's try to simplify and model this situation. Let's consider a game with three agents, Al Qaeda, FBI, and CIA. Each of them have two different potential actions, 0 and 1. 0 is to not act, and 1 is to act. The exact actions are presented here in this table. The game has two initial and two ending states. To model how FBI wasn't really sure about the agent's identity, we have initial state W prime representing how the two people weren't actually Al Qaeda agents, while in state W they were. Thus, in the diagram, we can see the dashed line or indistinguishability relation between W prime and W, and that's labeled by just FBI because, of course, CIA and Al Qaeda would know whether the identity of the two agents. And in final state V, the disaster, 9/11 disaster, did not happen, while in state U, the disaster did happen. We can see that each arrow is labeled by an action profile, which is basically just a tuple of three numbers, and these numbers actually map back to the agent's actions in the same order they appear on the table. So for instance, 100 would actually, or 100 to be more exact, would represent the Al Qaeda ordered an attack. FBI did not open an investigation, and that CIA didn't arrest anyone. Now let's recall, for the disaster actually have happened, the two suspicious agents must have been Al Qaeda agents, and Al Qaeda must have ordered an attack, and neither FBI nor CIA should have basically acted because they probably would have caught the agents, hopefully. In other words, for us to actually end up in state U, where the disaster happened, the initial state must have been W, the action profile must have been 100. And in any other case, we would have ended in state B. And to be brief, star represents any action. However, we're still missing the key piece of why we ended up in U. Why would FBI and CIA not act? For CIA, recall that arrest is an illegal action, so the question really remains, why did FBI not open investigation? Key is really the information wall between FBI and CIA, since without CIA telling FBI about the evidence, FBI couldn't have actually opened up an investigation. And in this game, we will be capturing it as a partition. Currently, this partition that we see on the slide has a single wall that separates CIA and FBI, with Al Qaeda on the same side of FBI. Technically, Al Qaeda could also be on the same side of CIA or even walled off into its own group, because being on the same side of the wall doesn't imply that Al Qaeda or anyone needs to share or volunteer any information to the agents on the same side of their wall. Since the exact location of Al Qaeda doesn't actually matter, we'll just choose this partition on the slide for now. And we'll call this partition sigma from now on. Thus, because of the wall between FBI and CIA, or in other terms, the sigma partition, Al-Qaeda has a strategy to achieve the goal of Flight 77 crashing into the Pentagon. Since we're in a game with imperfect information, we mean know-how strategies or uniform strategies whenever we say strategies. Basically, their goal has to be achievable in every single state that they can't distinguish. In other words, they have to actually know the strategy. Now let's move on to a media censorship example. Imagine that there are three agents, 逻辑, 知识, and 推理. They might be content or discontent with their current political situation. As a result, we have 2 to the third, or 8 initial states. In the diagram, we can see that each state is labeled by the attitudes of each agent in the same order as they exist on the slide. For instance, in state DCD, 逻辑 is discontent, 知识 is content, and 推理 is discontent. Each agent should know whether they themselves is content or discontent, but they would not naturally know the other two agents' attitudes. For instance, 逻辑 probably can distinguish that he's discontent from content, so he can distinguish states DCD and CCD, but he would not naturally know whether 知识 or 推理 is content or discontent without talking to them. So Logi can't really distinguish between DDC and DCD. And Logi's indistinguishability relations are illustrated here in the diagram. Similar to our previous example, each agent has two potential actions, 0 and 1. 0 is to not act or remain silent in this case, while 1 is to act or question the government. Naturally, if no one questions the government, then the status quo remains and nothing really happens. But suppose that someone, in our simplified setting, questions the government. Then it really depends whether the majority is content or discontent. If the majority of people is discontent, then we would have a revolution. However, if the majority is content, then whoever questioned the government would be thrown to jail and executed. Now, our agents are pretty rational and they don't want to just die for no reason, right? Just simply question the government, that's not enough reason to die. So we'll define a set of safe actions or actions that really wouldn't result in the death of the agent. Note that the legality of actions in our previous example, for instance, CIA not being able to arrest the suspects on American land, parallels the safe actions here. We can think of safe actions as actions that satisfy certain external or self-imposed constraints. Since each agent is different, the set of safe actions is also different for each agent. For instance, in state DCD, both 0 and 1 are safe actions for Logi, while in DCC, 0 is the only safe action. The diagram here are also labeled with Logi safe actions. However, Logi might not necessarily know whether 知识 or 推理 is content or discontent, so Logi might only know a portion or a subset of its safe actions. Hence, there's also a need to define a set of knowingly safe actions or a set of actions that an agent knows to be safe. Without any communication, 0 would be the only knowingly safe action for any of the three agents. Consider this partition tau 1, where none of the agents can communicate. Since there isn't any communication, all three agents would not be able to learn about any other new safe actions, if there were any. Hence, none of the agents would actually choose action 1 or question the government. Therefore, it is guaranteed or necessary that no revolution happens under this information wall, tau 1. And we represent this as a modality here, n. Suppose now that there is no information wall between 逻辑 and 知识, then in states where both 逻辑 and 知识 are discontent, like DDC and DDD, both 逻辑 and 知识 could potentially learn from one another that action 1 is safe as well. Therefore, under partition tau 2, there is no guarantee that revolution won't happen. In both of these examples, we've seen how information walls could potentially create new strategies for agents or could possibly change the outcome of the game. Now I'll hand off to my co-author who will explain the syntax, semantics, and technical results.
Wendy, thank you. Let me first summarize what Wendy said so far. Traditionally, when people studied interaction between strategies and knowledge, the paradigm was the more you know, the more you can achieve. The more the more information agent acquires, the richer set of strategies it can use, and it would know about those strategies that they're guaranteed to succeed. In this work, we're turning tables around. We look at the setting where less others know, the more you can achieve. When you acquire strategies from the fact that others don't know something, that others don't know that their actions, the certain actions that they have are safe for them, and therefore they don't use them. We formally capture this using models, which we call games, presented on this following slide. Those games have set of states. There is indistinguishability relation between those states, and this indistinguishability relation is agent specific, which is a way to capture knowledge of the agent. There is a certain domain of actions, and what is fundamentally new for this work is that for every agent and for every state, we specify a set of safe actions, assuming that agent only takes actions which agent knows are safe. So for every state and every agent, there is a set of safe actions, and this is item number 4 on this list. For technical reason, we also throw in one default action, which is always safe. So this way, agent always has at least one safe action. Our definition of a game also includes the rules of a game, or we call it mechanism. And this is just set of all possible triples, where first component of a triple is current state, second component is action profile, a function that assigns action to every agent, and the last component is the outcome. We do not assume that game is deterministic, so there might be multiple third components for the same first and second component, and also we do not assume that all games always transition to the next state. Sometimes they can terminate, and that's when there is no triple for given initial state and given action profile. Finally, as usual, we have evaluation function pi that specifies in which states propositional variable is true. The key to our formal semantics of strategic power into the dark are those two notions. The first of them is knowingly safe strategy. So in a state W, strategy is knowingly safe to agent A if it's safe not only in the current state W, but in every state which agent cannot distinguish from the current state. By KSWA, we denote the set of all such actions, knowingly safe actions. Now, the other definition here is a little bit tricky, and this is a set of DSW sigma. It's a set of all profiles, set of action profiles, in which all agents believe that they are doing something which is safe, or at least they might think that this is something. They might learn enough information by communicating with other agents that whatever they're doing would be safe. Now, sigma here is the partition of a set of agents. This is what defines those information walls. And we assume that each agent only can acquire information from the members of the same part of a partition, the same set in the partition as the agent. And that's the set of all such safe action profiles potentially known to be safe or distributively known to be safe action profiles is DSW sigma. There is one very technical notation that we use to define semantics is update of a partition. So if you start with an arbitrary partition and you pick an agent, then you can kind of isolate this agent into its own component of a partition. So that operation where you take a partition and you take an agent and put agent in the component of itself or herself that we call partition update, and we denote it by partition / name of the agent. Here are some examples of this. Now I'm ready to give you formal semantics. Points 1 to 3 as usual. Number 4 defines knowledge of the agent, and that's again as usual. Agent knows that statement phi is true in state W if phi is true in all states indistinguishable to the agent from the current state. Number 5 is definition of necessary modality. It's necessary under partition sigma. So if given system of information walls, given partition sigma, if everyone acts in what they think is a safe way, based on the information that they can acquire from the neighbors, from the members of the same set in the partition, they might come to a conclusion that this is a safe action, then phi will have to be true. And here's a formal definition for any action profile which is distributively safe, distributively known to be safe, and each state U, if you can transition into this state under this action profile, then phi will have to be true. Finally, the most important definition here is strategic power definition, that agent A under partition sigma has a strategy to achieve phi, and not only it has a strategy, it knows what the strategy is. If there is an action of this agent which is safe to the agent, such that for any state W prime indistinguishable to the agent from the current state, that's where we form the capture idea that agent A knows the strategy. So it should work in all W primes which are indistinguishable to agents from W. In all such states, if you pick any action profile where A acts as S prescribes, and where everyone else acts in a safe manner, known to them in a safe way, then phi will have to happen. Now there's an interesting point that in this dsW prime sigma / A, we have sigma / A. That's the update. That means that it's not actually under sigma, but under sigma / A. Why? Well, because A doesn't have to talk to others. A doesn't have to disclose to them any information unless they know, the fewer safe actions they have, and as a result, more strategic power A itself acquires. One other small definition, a finer partition. So if we have two partitions, we say that one of them is finer than the other if every equivalence class under the first partition is a subset of equivalence class under the second partition. Here are our axioms. So the first 3 axioms are kind of self-evident, right? We have axioms for knowledge, truth, negative introspection, distributivity. We also have distributivity for this necessary modality, and there is a monotonicity that if something is bound to happen under less fine partition, with fewer walls, then it's bound to happen with more walls, and the same for H, except it were adjusted for /A. There is also strategic introspection. If agent A knows strategy to achieve phi, then agent A knows that she knows this strategy. Most interesting axiom is known necessity. You can kind of see what it says over here, and if you want to get better idea why it's true, look at the proceedings. We discussed it in proof soundness there. For various axioms with inference rules listed on the slide, we can prove completeness theorem, and soundness and completeness are our 2 main results here. Thank you very much, and I hope to see all of you at AAAI 2023 in person.